In this video, I will go through several more examples of how to use KLEE, and the examples I will go through are small C programs that each have different characteristics, and interesting to see how KLEE reacts to them. So I will execute examples that explore kind of corner cases of small programs and see how KLEE reacts in that type of environment. I will not cover things like how KLEE reacts to memory vulnerabilities and how you can look for memory vulnerability primitives in programs with KLEE, and I will wait for that with another video because the subject itself kind of deserves a whole video in itself. So right now I'm in the KLEE Docker container that I showed how to install previously in the previous video, and I have created 6 small example programs that I'll be going through. So let's go through the first one. The first small example is simply a small program that has a main function here where we have a buffer of 10 bytes. It calls KLEE make symbolic to make the buffer to make the 10 bytes in the buffer symbolic, and it calls into Checkstring where we have a check on the 4 first bytes in the buffer for the characters test with capital characters. And in case that the 4 first characters in the buffer are indeed test, then we will get a bug. Here the assert 0 statement is a reflection of a bug. So the first thing we do is we compile it and get the LVM bitcode similar to previously. And we can then call KLEE on it simply by KLEE test1 BC. And we see that indeed KLEE found the assertion fail. So it prompts us the information that there is a place where we have a assertion 0 call, and there was 5 paths in the program, which corresponds to the 4 different conditional checks in our conditional statement, and 5 different execution paths corresponds to the 4 different cases where each of these can be, the first one can be true, then the first one can be true, but the second one false. Then we have a case where both the first 2 can be true, but the other one false, and so on. So all of these we have 4 different execution paths here, and then we have the case where none of these are true as well. And in total, there are 5 different execution paths in this function. Okay, so let's look at the artifacts produced by KLEE. We have 4 different test cases, and we can see the value of these test cases using the KLEE test tool. Here we have a buffer with all 0 bytes, so where none of the conditional checks in the Checkstring function are satisfied. We have the second one where there is a test case where the first buffer in the where the first character in the buffer is a capital T, but the next one is a null byte. And then we have a third test case where the second character in the buffer is an E, but then we have a null byte following that. Then we have a 4th test case, which is also the one where we find the error. And indeed, the first 4 characters of the buffer here are test. And then we have a 5th case where we have the first 3 characters of the buffer to be TES in capitals. So we can look a little bit more on the output of this assert error if we look into this file. It gives us the stack trace of where the bug happened, and it gives us the line number in the assembly code in the LVM assembly where the error happened. So if we close this one down, and just to confirm with you that the line where the error happened is line 50. So if we now go into the assembly.ll file, we can go to line number 50, which is here. And indeed we see that this is where the call to assert fail is. So KLEE is very good, and this is indeed in the checkstring function. So here we have all of the different conditional checks. So 84 in decimal is probably equal to the capital character T, and here we have the E, and we have an S, and then we have a T again, and if all these are satisfied, we get to here where we have a call to the assert. Okay, so we can also replay the test. I will show replay in just a second. Okay, so let's go to example number 2. Here we have a function quite similar to before, but a little bit of the substance of the checkstring is a little bit different. So we have our usual where we have a buffer here of size 5. We call KLEE make symbolic in order to make the bytes of the buffer symbolic, and then we call checkstring. In checkstring, we first declare a local variable sum to 1, and following that, we go through each character in the buffer array that we input up here, and we assign sum to be the value of multiplying sum with the value of the buffer. After that, we have a check here if the sum equals to 130, and if it does, we call assert 0, and here is the bug. So now it means that the bug only occurs if sum is multiplied up to be equal to 130. So this is a bit different from previously in that the bug is kind of indirectly connected to the computation that actually makes the bug possible. So here we do the computation that sums up the value, but the check occurs afterwards. So it's not similar to before where we had explicit checks on the bytes of the buffer. Here we actually do a level of a means of computation. There has to be a KLEE has to do something smart in order to find this bug. So let's see how KLEE reacts to this. We got our LLVM bitcode, and we run. Okay, and KLEE finds it pretty fast, and it also tells us that there are 2 different execution paths, and this is true since here we have in the checkstring we only have a single conditional statement, which means this is the only place where execution can branch to 2 different distinct execution paths. So indeed there are only 2 execution paths here. Okay, so let's look at the artifacts produced. We have test case 1, it's the one that finds our error, and test case 2 is the one that doesn't find error. So let's look at the values produced by KLEE in order to trigger the error. And here we have the data to be hex 1, hex 1, hex 2, hex 1, and then the ASCII character A. So that summed up should equal to 130 in decimal. So the decimal value of the hex of the ASCII character capital A is equal to 65, and 65 times 2 is equal to 130, which is exactly what the check was here. We can do the same thing in terms of we can identify where the error occurred on line 54 in checkstring. And indeed we have the call to assert fail here, which is where the bug happened. So KLEE had no problem figuring that little example out, which means that it can actually do the computation necessary to find out that the characters need to be summed up in the following way in order to produce the bug. Okay, so let's try example 3. In our third example, we have the exact same program except for now we have the value 257. So KLEE should pretty easily be able to solve this. Let's verify if we can do that. And it runs for a while. But it only runs actually for a short period of time. And it tells us that there's only a single execution path, which is a bit odd. But let's see why that is. So specifically, it tells us it doesn't report any information to us about that, whether there is a bug or not. It doesn't report any bug, which means that it also reports that there is no bug with the information that has been given to KLEE. And the reason for this is that the value we have here is 257. 257 is a prime number, which means that there are no two numbers or no numbers below it that multiplied together results in the value 257. Now, since a character can only be 256 different values, which means that's the maximum number it can represent, 255 in this case, it means that we cannot take any numbers below 257 and multiply them together in order to get the value 257. So this is actually a path that is not executable. It's a dead code path. We can never execute this statement. And therefore, that the fact that KLEE reports only a single execution path is actually correct in this case, because this one is not triggerable. Okay. Now let's go to our fourth example. Okay, so very similar again. We have a buffer here, and then we make our buffer symbolic, and we have a call to KLEE assume here, where we set the last character in the buffer to be a 0 byte, and we use KLEE assume to this. So we tell KLEE that we know that this character is this byte in the buffer is symbolic, but we assume that it is 0. So KLEE will treat it as a 0 byte. After then, we call Checkstring with our buffer, and then KLEE does a comparison. The program does a comparison with the buffer to KLEE is cool. And if the string is KLEE is cool, then we find the bug. So if KLEE is cool, we do find the bug. The difference here from the in this program in comparison to the previous examples is that we have this string compare function, and this means that which is a library function, and this means that we now test if KLEE can have how KLEE reacts to the fact that there are library functions in our program. So let's try and compile it. And run KLEE on it. So KLEE doesn't find the bug. And I don't want to go too much into the details with why KLEE doesn't find the bug, but essentially it's because KLEE has a mechanism to execute the string compare function outside the environment of KLEE. But we can also use something in KLEE that allows us to to include the string compare function inside the KLEE environment. And KLEE has this type of what we call a model of the string compare function. So let's go a little bit more into this and look at the symbolic environments. Using symbolic environments. The main we want to look at KLEE options, and here we want to look at the symbolic environment options, and we want to here KLEE provides several options as part of the this is not what we were looking for. We want to find something where we tell KLEE to the libc provided by KLEE, and I cannot find it now. I wonder where it is. Installing KLEE intrinsics. Well, I know where we have it for sure. Core utils. Okay, so we have this option to KLEE, which tells us that KLEE should use a specific libc library. And in this case, we want to use uclibc, which is KLEE's own implementation of libc that allows us to reason about symbolic bytes inside the string compare function. So if we call KLEE here, libc equals uclibc, then we find indeed that there is an assertion fail. And this is because now KLEE can suddenly reason about the symbolic inputs, reason about symbolic bytes inside of the string compare function, whereas we couldn't do that in the previous run. So if we see in our KLEE last file, we get that there is we get the error case here. And we can see that KLEE reports to us that indeed KLEE is cool, so we find the bug. And we can also see the other test cases where we have various different bits of the KLEE is cool string. And the reason for this is that now KLEE can suddenly do this comparison inside the string compare function because we included its implementation of string compare. So it has this so it can indeed show us that there are multiple execution paths depending on the value of the buffer, since there will be some type of compare statement inside of the string compare function that checks each character if it is the same. Okay, so this is a way that we can actually use uclibc and have KLEE treat have KLEE handle symbolic bytes inside of common library calls. Okay, so let's go to the next example, example number 5. Okay, so here I have a separate example where we have a main function. It calls the get value based on time. This function get value based on time declares a struct called raw time. Then we declare a time info struct, and then we get the time essentially on my local computer. It prints out the time, and then at this point we make the bytes of the buffer with the time info symbolic. So we have a KLEE make symbolic in the middle of a function instead of having it as we did before at the very beginning of the main function. Now we have the KLEE make symbolic inside of a function, which is perfectly legal. There's nothing that hinders us from doing it, and we don't at all need to have the KLEE make symbolic in the beginning of the main function. This is interesting because you can think of having large code bases where you just want to make very specific parts symbolic, and without having to make the symbolic and get your symbolic value into deep in the program. Instead, you can treat it very locally in that sense. So let's see how KLEE does this. And also the bug only occurs if the minutes of the time is equal to 12, which is not the case here. It's 21:31, so we are far from being close to 12 minutes. And we should be able to find the bug here, but let's see how KLEE reacts to it. Okay, that's fine. And let's call KLEE make symbolic. And sorry, let's call KLEE on it. And indeed we get that there is an assertion fail. And so KLEE finds it, which is awesome. And indeed it shows that there are two different execution paths, and the reason for this is that there's only one conditional check here, and that's essentially it. I don't want to go into any more detail with this example, but go further to the next example. And in this case, we have, it's the exact same example as the first example, but we have no calls to KLEE make symbolic. So what I want to show in this example is that how do you get symbolic input from outside the program into your program. And this is a nice feature because KLEE can pass symbolic input from the command line, and this is what we're going to show in this case. And there are several benefits to doing it this way, as it can have the benefit that it's much easier to replay the bug on the executable file, the real executable file, which I will show afterwards. Okay, so first we get our LLVM bitcode, and we can run. We do not want to run KLEE on it yet. First, we want to check out on the documentation. We want to check tutorials, and we want to use symbolic environment. Okay, so KLEE has this symarg command line, and we note that symarg provides a command line argument of length n to the program under test, and the buffer that we provide here will be a symbolic buffer. So just to look here, that it expects at least 4 bytes, but let's just give it 10. So that means we call KLEE in the following way. This should find the bug. Oh, we need to do it on the LLVM bitcode, and it does not. Oh, this is because we need to include, we need to run KLEE with the POSIX runtime as well. So, what happened here? Okay, so we need to also include this flag whenever we want to give symbolic input from the command line. And it goes, and indeed it worked. We got a lot of test cases here. And let's see the error file. We get that here. So we use our ktest tool on KLEE out 1. And let's just grab it like this. And we can see that indeed it finds the correct buffers here. Test. So that works very well, and we get the error. Now, the last thing I want to talk about in this case is, in this video, is how do you actually take the values from KLEE. So we have found an error with KLEE, which is this one, 72, test case number 72, and we have these bytes will cause the crash in the program. But how do we actually replay this on an actual executable file and not necessarily the BC code? And the way you do this is, first you compile your program. So you have now the executable file, and we can just test for ourselves that if we point test, if we give the argument test, indeed we get an assertion 0. But if we want to, if it gets more complex and we just can't pipe the input in the following way, how do we actually do that with KLEE easily? And KLEE has a tool called KLEE replay. And let me see if I can find the documentations. Okay, I've just lost it here, but otherwise I can do it. I just had it before. So we want to look for the KLEE replay tool, and it should testing core utils. Okay, so KLEE has this KLEE replay tool. And to use the KLEE replay tool, we just tell it the executable to run and the ktest file to use. Okay, so we call KLEE replay here, and then we have the binary executable here, and then we have the test file here that we wanted to replay with. So we have the KLEE replay tool right here. We have our executable program which is called a.out in this case, and then we have our test case number 72. So let's see what happens in this case. And we get a KLEE replay information here, and we also get the run of the executable application here, test assertion 0 fail, which corresponds to the output that we got previously when I ran the program just with test right here. So in this way you can replay the test cases that you find with KLEE, which can be pretty convenient when you want to try the input found by KLEE on the executable itself. Okay, so this is it for now. In this video I showed a few examples of how to use KLEE against various different applications with different characteristics, and also showed how you could replay test cases found by KLEE, how you can do a little bit of analysis on the resulting on the LLVM files and see where KLEE locate where KLEE finds the bug inside the LLVM files by looking at the line number where the bug occurs. Thank you for now.